Okay, Falstad is a great tool for showing current, how it flows in a more complex setting here. And I meant to add some series, so hang on just. Okay, so obviously this has got some series resistances and some parallel resistances in it. And we speed up this current speed a little bit so we can actually see current flow. And this gives you some concept of how current's flowing. Obviously, we got a lot more current flowing through this 1K than we do the 2.2 and the 6.8. And that's because current's right here. Of course, all current is going through this point, and that's why I've got current meters in both behind and in front of the 47K, is so we can see that it's an equal amount of current. And if we add all of these up, they're going to add up to this total right here. And that's because these are just like electrons flow about like people do in Walmart. If this line is pretty fast, people are going to go pretty quickly. If this line's a little more slow, people are going to go a little more slowly. And if this line's the slowest of all, then people are going to go much more slow. So less resistance, a little more, and a little more. We would navigate to the lines that would move closer until that line got really long. Then we go, okay, well, we're probably okay here. And if that line got fairly long, we'd go, okay, well, we're probably okay here. Cashier might not be as fast, may have more resistance, but if there's a shorter line, then we can get through it at about the same rate. And that's how electrons flow, for lack of a better descriptor. And so here we see this, and of course to solve this circuit, and I know why the current's in the microamps, I'm going to edit this one, so just disregard the currents. The value will hold true, but I wanted that to be a 4.7K, not a 47K. So I wondered why that was going so slow. Now it's going fast because I had to speed it up. There we go. So we know that this source is a 12-volt source. And we know total current because I put these meters in here. So we can figure total resistance just by doing a calculation. We can take 12 volts and divide it by 1.868, and that's in millis, 1.868. And this is going to give us the K value. So overall, our total is 6.42K. Now we're going to prove that, and we're going to write this down just so you can see it. So our total equals 6.42K. Alright, apparently I write well in pink, because that's not half bad. So now we're going to first we always have to solve the parallel, so we're going to get the parallel branch equivalent here. So we're going to take 1, we're going to reciprocate it, plus 2.2, and we're going to reciprocate that, plus 6.8, and we're going to reciprocate that, and we're going to equal, and then hit reciprocal. Now we know it should be less than 1K, and it is. It's 624 ohms, or 0.624K. So I'm going to put parallel branch. I'm going to abbreviate that branch just to save writing, is equal to 0.624K. Now, we're going to add all of this up, because here's what happens next. We've got to add that 0.624 to the 1.1 and the 4.7. So I'm going to keep it fairly clean and just say 0.624 plus 1.1 plus 4.7 equals 6.424. So look at there, we lined up. So we proved that just by using Ohm's law, and we validated it 2 different ways here. So we can see that. We could also unhook the source and unhook some things and actually measure with an ohm meter across these parallel branches. But we can do that even so. I'll come down here and draw a resistor, and we'll add one, another, and another. And we'll have to connect the dots here real quick. Remember, we have to go dot to dot. And I'm going to draw in where is it? It's hard to see with the writing on the screen here. Right there, an ohm meter. Oh, drat it. Here we go. So there's our ohm meter. I'm just going to draw some wires, and we're going to measure those three resistors in parallel. And oh, I didn't change the values. I was wondering, that's not right. So that one's right. So let's make this one a 2.2. And let's make this last one a 6.8K. So there we are, 624 ohms or 0.624K, same value. And we proved that these are there. We just add that to the 1.1 and the 4.7. Remember, 1.1 is really 1100 ohms, 4.7 K is really 4700 ohms. So we just have to switch between units. But we proved it all the way around. We can see how current flows through this guy up here. I'm going to, whoops. Get rid of this guy at the bottom so he doesn't aggravate us. I thought it was. But anyway, so full current going through this resistor, part of that current going this way, then part of that current going this way, then part of that current going this way. And I'll show you one more thing while we're here. We'll throw in a couple more ammeters here. And it really doesn't matter if I do them on top or on bottom. But notice this 1.8 that I've got here. 1.1 goes that way, and it leaves 700 microamps, or 700 0.701 milliamps, depending on which way you want to look at it. And then, when we get right here, 530 of those microamps go that way, and 171 go this way. So these two add up to that, and this add up to that. So this is the current split. So let's follow that. 1.8 milliamps till we get to this junction. 1.1 goes this way, 700 micros go that way. 700 micros at this junction, 530 go that way, 171 go that way. So should be able to do that math as well, and that lets us see some things that we might not have thought about before too. So as always, questions please ask.